Okay, so in this video, let's try to use the same model that we used earlier, but this time we will assume it's a mat foundation. So remember, this is our isolated footing earlier, but remember, for a mat foundation, there are multiple reactions, okay, on your mat footing, okay? So in this case, we have 4 reactions applied to our footing. So it serves as a mat foundation already. And say at this point, we have a 400 kilonewton and a 300 kilonewton downwards. But this time, we will now apply a moment. Okay, so moment about Z, 52 kilonewton meter. Okay, so something like this, so 52. And then another on the 300, we have another 15 kilonewton meter. Okay, so here we have 500 and 250. Okay, so this is a typical situation for a mat footing. Okay, you have multiple reactions applied on your foundation. Okay, now the rest is the same. The properties is the same, 700, except that there's a new loading. And then let's, by the way, the supports is still the same. I assumed a subgrade modulus of 50,000 kilonewton per cubic meter. Okay. And let's now analyze. Okay, and then let's check the displacements. Okay, so the displacements, the maximum displacement is here because as you notice, the 500 kilonewton concentrated load, that's the largest concentrated load applied, it's on this location. So it makes sense that the maximum displacement is also here. Okay, so the value is 3 mm, negative 3.3 mm. So which is here, okay, 3.3. And how about the minimum? Negative 0.679, so somewhere here. So this is the, the maximum settlement is here, the minimum is here. Okay. For the base pressure, plate results, base pressure. Yeah. So also makes sense that the maximum base pressure is also here, 165 kilopascal. Okay. The minimum base pressure is on this edge, which is 34 kilopascal. Okay. So remember, by using 450 kilopascal SBC, we were able to derive a 50,000 kilonewton per cubic meter subgrade. All right. And as you see, since the base pressure is less than 450 kPa, so that means our mat foundation is safe, as according to its allowable pressure. Now, let's now proceed with our Matlab code. Okay. So this is now the Matlab code. It's the same. Okay. except that we now have new forces. Okay, so these are our forces. So let me go back to our loading here. There. Yeah. And shift N for the nodes. And here. So to make sure that it's consistent. So the 400 kilonewtons, this one, applied at DOF 163. The moment 52 kilonewton meter is this one, applied at degree of freedom 165. The 250 kilonewton is this one, applied at degrees of freedom 703. This one is 300, this one, applied at degrees of freedom 193, and with a 15 kilonewton meter moment applied at degrees of freedom 195. And last one is 500 kilonewton applied at degrees of freedom 670. So how do I check that? So for example, this 250 kilonewton meter, that is applied at node 235. Remember that node 235 times 3 is what? Okay, so that's 705. So the vertical DOF there is 703, while the rotational DOF is 704 and 705. Okay, so that means at node 235, the vertical DOF is 703. That's why it's applied at 703. Okay. Now, for example, here with the moment, let's check the moment. That it's applied at node 65. Node 65. Okay, so 65 times 3 is equal to 195. So that means that is the rotational DOF. Okay, 195, which corresponds to our moment. Okay, and then therefore the vertical DOF is 193. Okay, that's why the 300 kilonewton is applied at 193. Okay, so that means the mx moment will be at degree of freedom 194 if you have a load mx. Okay, so that's it. So basically that's the only modification in the code. Okay, so the rest is the same. No? So let's run this, and this is our corresponding the deformation. Okay, so which is consistent with STAAD because the vertical displacement is somewhere here, so the minimum is somewhere here. One edge is this one, another edge is this one. Now let's verify the displacement. So for example, on the displacement, this is the maximum displacement at node 273, which corresponds to what DOF? So at node 273, The displacement is 3.31 millimeters. Okay. 273. So what's the DOF for 273? So times 3 minus 2. 817. Okay. So let's check the vertical displacement at 817. So the same. Okay. So that's negative 3.3 millimeters, which is the same with our STAAD. How about here? Node 33. So that's 33 times 3 minus 2 is equal to 99 minus 2, 97. So that should be 0.681 millimeters. Displacements 97. Yeah, so that's almost the same, 6.7 millimeters, right? This is 6.7, 0.67 millimeters, okay? Because this is in meter. So that's 0.67 millimeters. And maybe last, how about this one? Node 1 is, of course, displacements 1. It should be 2.895. Yeah, so it's the same, 2.9 millimeters. So in terms of displacement, our Matlab code is the same with STAAD. Okay. Now, how about plate results? Global moment. About X. Okay. So we're now seeing all the moment on this direction. Right? So remember, we have vertical loads here. So of course, the stress concentration is on this point. Okay. So that's why the negative moment, maximum negative moment, is the magenta. So 75 something here, magenta to blue. There, and this one, these are all positive moment in terms of STAAD's invention. So these are negative moment, and this one is positive. So when you this is also positive. Anyway, if you create a section line here, what we will see is something like this, right? We have a negative moment and a positive moment, right? Now let's check with our code. For example, this is plate 200. Let's check the moment we got using Matlab. Moment of plate 200. So in STAAD, we're getting 70 and 10. Okay, mx 70, 71 kilonewton meter per meter for mx, for my 10. So which is the same with our code. Okay, so how about on the negative moment side? So let's double click here. Plate 194. Plate 194. STAADs gets 41 and 63. Our Matlab code, we're getting 45 and 65, which is very near to each other. And maybe last one here, another negative moment here. 18 and 24. So that's plate number 222. Yeah, so almost the same, 18 and 28. Okay. So therefore, our code is verified correct, in terms of commercial software STAAD for both MXMY and for the displacements. So using the same code we used earlier on isolated footing, we can create, or we can use the same code to analyze a mat foundation. Okay. And maybe last one is the soil pressure, the base pressure. Plate results again. Base pressure. So consistent with the displacements, the maximum displacement is here, which is what do we get here? Displacement of 817, right? Yeah, 3.3 mm. So that, since this is a maximum displacement, so consistent, the maximum pressure is here. Okay. Now remember that the earlier derivation in stiffness is we idealize a spring per node, right? And we found out this is 78 1 250, right? 250 Newton per meter. Okay, 78 250 Newton per meter stiffness per plate. Okay, and the tributary area is this, right? Now, since we are checking the base pressure per node, therefore, to get the force, the force at that node, we simply multiply the stiffness, which is our K, 78 250 times 4, right? Which is majority of our plates are in the interior, so that's times 4. Because, for example, if we wanted to find the base pressure here, there will be 4 plates contributing to the stiffness, right? On that node, and on that interior node. So the stiffness 78 250 times 4 and multiplied by the displacements, right? From the basic formula, F is equal to K delta, right? So to find the force, multiply the stiffness by the displacement. And the displacements are known already. We have already solved that. So displacements at that corresponding node, vertical node, no, vertical DOF, divided by the, maybe, yeah, that's just a force. No, but since we are dealing with pressure, base pressure, so that will be force over area, right? So basically, you use this divided by the area. And what's the area? It's simply A squared, because our plate or our mesh is a square, right? It's a square plate having A, which is 0.25. Okay. Or basically, that's the formula. So what I did in Matlab is this one. You can so this is the formula now. To compute the base pressure, we have, for example, if you wanted to find the base pressure at DOF 670, so this is the formula, 78,1250 times 4 times 1,000 to convert into kilopascal. And the displacements at DOF 670, it depends on you what's the location you wanted to find, okay? And A squared. 1,000 square because our A is in meters. So to convert into millimeters, that's 1,000 square. So that's it. So let's check, for example, node 257. So I'll be copying this here. And so let's try to find the pressure at 257 or say 240. 240, what's the DOF for 240? So say right here, 240 times 3 minus 2 is equal to 718. So that's 718. 718. So I'll change this to 718. Okay, so I'll be getting the base pressure at node 240. So enter. So I'm getting 153 kilopascal. And upon looking at our contour, if you check, that's about between 149 to 157, which is 153 kilopascal. Okay. How about say on this blue here? Let's choose node 43, for example, node 43. Or no, node 44. So somewhere in the blue. So node 44 times 3 minus 2 is equal to 130. So DOF 130. Okay, so I'll copy this again, paste here, and then I'll call DOF 130. Okay, then enter. So that's 78 kilopascal, which is node 44. The blue color is, yeah, between 75 and 83, this one, between 75 and 83 kilopascal, which is correct, 78 kilopascal. Okay, so which means that's how you compute for the base pressure. So looking at the graph, we are getting our graph, our contour, stress contour. The maximum base pressure is 165 kilopascal, as you can verify, and the minimum is 34, which means we did not exceed the allowable soil bearing capacity, which is 450 kilo pascal. So that's it. So again, by using a thin plate, so this shows that a thin plate bending element with a 12 degree of freedom can be used extensively to plate, steel plate, to even isolated footing, and even mat foundation. And again, when you wanted to design the rebar for this, remember, you just have to call out the moment and get the moment and use that to design your rebar. Simply, when you have the moment, you can use this formula, PRBD squared, wherein you can get the R, and then you can get the rho and the AS required for the design. Okay,